Welcome to the second part of the lecture series for week 5. And here we'll discuss a bit more about the building blocks and the terminology of control theory. We'll look at an example of control theory in practice right after this slide, and I will show you how to model a mass spring damper system if we model it in a block system. So let's start with the example of the automated flight in practice. Now, this is a student project. I've put the link in the slide, and this PowerPoint presentation will be on Brightspace as well as this video, or the link to this video on YouTube. So have a look at the whole video. I'm going to show you the introduction very briefly, but I would like you to have a look. This is the source, and let me just pull that up, and here we go.
I just wanted to do a quick overview of the project we've been working on. This is a simulation of a quadcopter that we have built a physical model for. This simulation has everything from command inputs to control outputs, as well as the dynamics model that displays how the quadcopter would behave. We start with an input from the pilot, which we are using an Xbox 360 controller just for simplicity. It has the two joysticks, the same as we would use on a FM receiver, or transmitter and receiver. From there we go into a mode logic, which we have different selectable states so that we can control things from accelerations to positions or velocities. The mode logic takes...
And I'll just stop it here. Here. And what you can see here is his the project group's model, and what you saw were different blocks and different arrows. Excuse me. And what I would like to do is now share with you the terminology that we're going to be using. Now, so the arrows denote a signal, and the arrow direction denotes the direction in which the signals can travel. They can only travel one way. Now, usually a block is reserved for some system, and in that system it will either have a name, its function, but typically for control theory, the name of the transfer function that we're dealing with. So we have signals and systems. Now, these signals can branch off at a certain spot where you basically split the signal into two equal paths. That's called a branch point, and we can also have situations where they come together, and that is called a summing point. And of course, we can add them together, but we can also subtract them. So in this particular case, we would have that the signal S3 would be S1 minus S2. And of course, you can have as many signals coming together and branching off as you like. But for a summing point, usually there's a symbol, a big circle, where you indicate the signs of the different signals. Now, if we have a system with input and output, I've written an example like this. This is an open loop system. It means that there are no loops, like in the next example, where we have an input. I've called the input U, I've called the system G, and I've called the output Y. Of course, different letters can apply to different situations, but one of the things I'd like to emphasize is that if we do this in the time domain, finding the relation between the input and the output can be extremely difficult. In fact, what you need to do is use the convolution integral, which is a lot harder than what we can achieve if we use the Laplace or the S domain, where we write everything as, in terms of S, our complex variable, and then we can simply write that the output is G times the input U. And I will make these capitals. I will make a proper capital Y. Because Laplace transformed variables, we typically use capital letters. But in the S domain, running an input through an through a system to get an output simply results in a multiplication. Now, another example is we have a cascaded system. So we have an input going into one system, then going into another system. Well, I have U1 here and its output Y. Signals are typically denoted as in lowercase letters. But in this case, we know that the output Y is equal to U1 times G. So Y1 is G times U1. But if I want to know the output Y2, well, I also know that Y2 is G2 times U2. But as U2 and Y1 are the same, I know that Y2 is simply G1 times G2 times U1. And so if we have cascaded blocks, it ends up with a multiplication. Now if we have parallel blocks, we have that our Y is equal to G1 plus G2 times our input. And so parallel blocks end up being summed. So we have multiplication in the case for cascaded systems, and we have summation in the case we have parallel blocks. But now we have this feedback loop where we have a reference signal, we have an error term, and the error term is what drives the system. Let's say we have a thermostat for a heating system. We have a set point of 21 degrees. We have an output temperature which is, let's say, 18 degrees. Then we have an error that we feed into our heating system, and that will heat it up. And of course the error becomes smaller, and at a certain stage we hope to reach our desired temperature. Now here I've added a feedback controller. I've called that H. And what we know, we can write out the formulas because we want to know what the transfer from the input to the output is. So that's the transfer function of our closed loop system. So eventually we want to know Y of S over R of S. This is our transfer function. Now how do we start with that? Well, let's first note that our error signal is our is our reference signal minus whatever the controller did to Y. I also know that Y is equal to G times my error signal, because that, if we want to go from here to here, we only pass through G. Now, if I substitute my error signal here for this, what do we end up with? I get Y is equal to G times R minus HY. I can separate this out, is equal to G times R minus G times H times Y. I will now transfer this term GHY to the other side, and I find that 1 plus G times H times Y is equal to G times R. And now if I want the transfer function Y over R, I find that this is equal to G divided by 1 plus G times H. And I've omitted the S's, but we know that these are all functions in the S domain. But if I have a feedback loop, that is one way of dealing with it. Well, this is, sorry, not dealing with it, this is the way you find the transfer function from the input to the output. Now, something else we might want to do is not only look at these, well, these general systems, but let's look at our mass spring damper system. we have that m x double prime plus b x prime plus k x is equal to some input f. Now, how do we turn this into a block diagram? Because if I have the system, I start with f, I put this in the system, and eventually I want to have my x. Well, we will do this, we could do this in the time domain with symbols, and I will start with that one first. But first we need to rewrite this, and I'm going to give myself a bit more space here. I will first divide the whole equation by m, so I get x double prime plus b over m, x prime plus k over m, x is equal to f over m. And I want to have the displacement x, but I have now, well, I can rearrange this so that I get x double prime is f over m minus b over m x prime minus k over m x. So basically these two terms are transfer them to the right hand side. So now I have the second derivative of x, which is nice, but I wanted x. I do know that x prime is the integral of x double prime, and x is the integral of x prime. So these are the steps I can take to reach x from x double prime. So let's see. Let's say I have here x double prime. I can put that into an integrator where I get x prime, and I can put that into another integrator and find finally our output f. But what do we have to do here? Well, if we take a look back at this bit here, if I have f as an input, I can, let's see, I can multiply that by 1 over m and I will need to add a bit more, because now we only have f times 1 over m, but we still need to subtract b over m times x prime and k over m times x. But I have x prime here. So if I multiply this by b and subtract that there, I will add the 4's. Then I already have 2 of the 3 components. I now need my k times x, which I'll put here. And I will also subtract that from this. So what I've done is I've taken my differential equation, rewritten it in terms of the output variable I want, well, unfortunately the second derivative of that. I know I have these relationships here, where now if I put this all together, I will now have f minus bx prime minus k times x, and then I multiply those all by 1 over m, then I get my x double prime integrated, and I have my output. Now, if we were to do this mathematically, these integration signs, well, these blocks will be very complicated. The nice thing about the Laplace transform here is that an integrator in the time domain is simply a factor 1 over s in the Laplace domain. So finding the block diagram of a differential equation is rather straightforward. And also, if we want to add things like controllers and everything, we can use these rules very easily in the S domain, but not so much in the time domain. So this is an example of how we can use our block systems. I will skip through a number of slides here to, let's see, this point where we and we've seen this slide before. This is the impulse response of a second order system. Let's see. And I really wanted, not this one. This is a PowerPoint where we discuss certain things about loops and cascaded and summing of blocks. And I will just quickly scroll through these. This is again a form where we don't use a mass-spring damper system, but simply A, B, and C, and how we can derive the block diagram for this. So if we look at a second order system, just as any second order system where we have as a transfer function 1 over 2s squared plus 0.5 times s plus 1. And this just is the system where we have on the board where we have our G. The relationship between the input and the output. Now, as an input now we have a step function. But in the Laplace domain, we're simply multiplying. So if we want to see what the Laplace transform of the output is going to be, it is simply multiplying our transfer function by that input, 1 over s. In Mathematica, which we don't use, we can see what it was, what the step response is, but let's model this in Xcos. And we saw this before as well, where we have our input as a step function. We have the system under consideration, 1 over 2s squared plus 0.5 times s plus 1. And we want to look at the input, the step response, and the output. So we use our multiplexer to have two signals that our oscilloscope can then disentangle. And what do we see? We see this step response where there's some oscillations. We've also set the step to only start at 1 second. So there is a slight time delay in our system. Now, I don't want to discuss too much now about stability and unstable systems and that, but I want to look at some properties of this some terminology and properties of such a step response. And a step response is very important in control theory, as is an impulse response, because we see the properties of our system. Basically, we see its behavior. Now, so if a system is has a step input, like a system is turned on, or we have a level change in an aircraft, it will have an initial response, a response to the system that will eventually die down, and this is called the transient response. And here we see a large overshoot and some oscillations before it finally settles down. And settling down formally we call the steady state response. Once all transients have died down, we see that the steady state response is the desired response because it now has reached our reference, our step, which in this case is 1. So to get to our reference, to get to the height, in this case 1, it takes some time to get there, and the time to get to about 80% of our reference value is called the rise time. Now, some systems you want a very fast rise time. Sometimes it doesn't really matter, but in, let's say, level changes in an aircraft, you don't want to go up too quickly. But what you also don't want is to have an overshoot. Here we have a clear overshoot of at least half of our level change, and that of course will be unacceptable. Now, once everything has settled down, which means that it has become within about 10% of our reference value, that is called the settling time. And after that, it will come closer to our reference value, but it might still have a residual error. And this is called the steady state error. So we have a transient situation where we have a rise time and overshoot. It settles down into the steady state response, where it might still have a residual error. So what do we mean by overshoot? It's the amount of the response that exceeds the desired response. So we had a reference step of 1, and the overshoot is the amount that it goes over our set point of 1. Well, the steady state error is the error that's left between the system and the reference after everything has settled down, after everything has decayed, and we might still be left with some error. The rise time is the time for the system to reach about 80% of the reference value. So these are formalized versions of basically, let's see, of what we see here. The different properties, we can now add numbers to it. And these are also design criteria. You might not want to have a system that is slow or overshoot. So we can define our design criteria saying we want a rise time of 1 second, we want a maximum of 10% overshoot, we want a settling time of 10 seconds, and we want a maximum steady state error of 1%. These are design criteria, and you can design your system and design your controller to meet these criteria. All right. So the transient response, the response of a system as function of time, but yes, only up till the settling time, which is the time it takes, and now I'm in the way again. It's the time it takes for the system to reach about 10% plus or minus our reference. Up to then, that is the transient response. And of course, we want the transients to die out as quickly as possible. Of course, we don't want to race from one level to the next. Being in the back of an F-35 fighter is going to be a much different experience than being in the back of a Boeing 737. They are different design criteria. All right, so this was the first video about automated flight in practice. So we saw a video of a student group. Have a look at that video, watch the rest of it, it's very interesting. We then defined some terminology for signals, for systems, and how we can put different systems together. And we had an example of a mass spring damper system over here, where we saw how to get from the differential equation to a system in the Laplace domain, where we use our blocks and our integrators in the Laplace transform. We saw how to calculate the parallel cascaded and the feedback loop responses, and of course the basic definition of a transfer function, which relates the input to the output. But I will write that down just one more time. The transfer function of a system G of S is the relationship of the output over the input, all in the Laplace domain. And we will see that we can have a transfer function of an open loop system, a closed loop system, and all kinds of ways of cascading and parallel summing blocks all together. So we will continue this in week 6 through 8. We will expand on this and also see how we design a controller to meet the criteria we discussed in the PowerPoint. So this is it for now. In the next videos we will discuss mass spring damper systems and discuss them not just in terms of a damping coefficient and a spring constant and a specific mass, but more classify their behavior and look at what kind of behavior we have for what we so-called damping ratios, and so that we can classify systems not in terms of the specific constant, but in terms of behavior.